Okay, we're going to go over types of nuclear decay, particularly how to identify them from nuclear equations. The first type I want to talk about will be beta decay. Now, the key is the term decay. Decay means that something is being released. In this case, it's going to be a beta particle. An example would be carbon 14, producing nitrogen and a beta particle. Have that production of a beta particle. Another example would be nitrogen. And again, we have the production of a beta particle. I'm going to write the beta particle in a different symbol just so that we can see that it's still the beta particle. Now notice, just as we discussed before, that your masses and your protons must equal on both sides. We have 14 on the carbon side for mass, and then nitrogen 14 plus 0 from the beta particle equals 14. In the reactants at the top, we have 7 minus 1, and that will equal 6 atomic number on the reactant side of the carbon. Okay, but the key here is that beta decay produces a beta particle. Let's look at alpha decay. And again, as the name suggests, one of the good things about these is that the name is pretty given. It tells us what it is. It is going to produce an alpha particle, which means that the alpha particle will be in the product. So an example of this one, let's look at radon, or I should say radon. And this will produce radon and that alpha particle. Okay. Alpha particles on the product side. Another example, I'm going to write the alpha particle in a different order, just so that we can see. It doesn't matter the order that they are in on the reactant side, just as long as it's on the reactant side. Okay, and this one is going to produce land. Our masses equal across the top, our protons equal across the bottom. I believe that the next one that you had was an electron capture. Unlike the decay, a capture indicates that the electron or beta particle will be on the reactant side. Okay, so it's being captured by the nucleus of the atom. An example of this, let's look at arsenic. And we have our electron on the reactants being captured by the nucleus. And that electron will actually combine with a proton, which will take a proton out. So that means that this will decrease in the atomic number, but when it combines with that proton, it will produce a neutron. So the mass will remain the same. And we have germanium. This is our electron capture. Now, this is different from nuclear fusion and nuclear fission. Nuclear fusion, let's start here, is where we have two nucleus join. I should say two nuclei combine. So in this case, let's look at hydrogen is a very common one of the reactions that fuel our sun. Now I am going to have two atoms in the product, not an atom and a particle, but two atoms in the product, in the reactants, excuse me, that will combine. These two protons combine into two. That's the main thing there. They will combine into a single element in the reactants. Now, the mass may not add up to equal the two individual atoms in the reactants because we tend to always form a neutron. So depending on how many neutrons we form, that will determine the mass. But the protons will equal the protons of the products will equal the protons of the reactants. So let us do another example so that we can see. Let's use a different isotope for hydrogen. Let's combine these two isotopes for hydrogen. Again, we are going to form helium because we have the two protons. And this time, I will tell you that this will be a direct alpha particle, so to speak, the 4 mass, and we will, let me get rid of that extra plus. We'll also have a neutron. So let's compare this to fission. In fission, we have the nucleus splits apart. It forms 2 or more new atoms. I am going to use uranium-235. And in this case, when we have fission, something happens to this uranium to make it want to split apart. Usually it is that it is bombarded with a very, very, very high energy, very, very extremely fast moving neutron. That neutron hits that uranium and poof, splits it apart, releases a ton of energy. The first one, we're going to have strontium and xenon. Now, with nuclear fissions, we have additional neutrons that are formed, and these neutrons continue on to bombard other radioactive isotopes to cause other nuclear fissions to occur, and this is what we call the chain reaction. And in this case, if we add everything up across the top and across the bottom, we will learn that we actually form 2 additional neutrons to continue on the chain reaction. Let's do another example using uranium-235 plus that high-powered neutron. You may or may not see this in the reactants, but you will definitely see at least, or I should say, the one radioactive isotope in the reactants that will split into 2 new isotopes, more stable isotopes in the products to symbolize nuclear fission. And this time, as a 55. And we're going to form 3 neutrons in order to continue on the chain reaction. And so just a quick comparison, we see that for fission, we have 1 isotope that splits into 2 stable atoms plus neutrons. And then for fusion, we have 2 isotopes that combine into 1 atom. However, for our decays, electron capture, alpha decay, and beta decay, we literally have an atom on one side, atom on another side, but we have particles. So either it's going to be, for decays, it's going to be an atom that produces an atom and a particle. And for a capture, it's going to be an atom and a particle that produce an atom. So that is how you tell the difference between them. Let me know if you have any other questions. You know I can talk about this all day.